So firstly, I want to thank the organizers for giving me the opportunity to present my group's work here. This has been like an impeccably organized conference, so truly thank you. Okay, so yeah, I'll be talking about work that we've been doing at JILA, continuing on this theme of trapping alkaline earth atoms in tweezers. Oops. We good? Yeah? Okay, cool. So just in case you slept through your alarm, which would be very sad, I'll be continuing using this technology of optical tweezer arrays, which this is a practice in which we use microscopy and spatial light modulation techniques to trap and detect individual neutral atoms. This is based on pioneering work in the Grandier group in the 2000s. So these systems have been used for a variety of applications in quantum science based on the capabilities that they afford. So for instance, we just heard about how they can be used for many-body physics. This arises because of the programmability, scalability, and the possibility of using many different kinds of interactions in these systems. There have been a variety of experiments also leveraging these capabilities for quantum information processing. My group, Emmanuel's group, has explored how these tweezer array systems can be used for studies of metrology. And finally, I want to highlight these recent experiments out of the CUA where the ability to precisely position single atoms in tweezers has allowed for studies of interfacing single atoms with nanophotonic devices with very, very tiny mode volumes. So a lot of the work over the past decade or so has really focused on alkali atoms, so atoms with a single electron in their valence shell. And one theme over the past 5 years or so has been expanding this tweezer toolset beyond that paradigm. So this is exemplified by efforts, say, at the CUA for trapping molecules in tweezers. There are beautiful experiments from Hannes Bernian's group at Chicago where they trap different alkali species at the same time in different tweezer arrays. And finally, our work at JILA, Manuel's group at Caltech, and Jeff Thompson's work at Princeton, we've all been exploring this idea of trapping two-electron atoms in tweezer arrays. And let me highlight as well that this is an exciting direction with I would maybe describe as frightening number of groups beginning to explore this as well. Okay, so in my group, we've been exploring a couple different things. These include quantum metrology and metrology of atoms in tweezers. We've been looking at new ways to study and control Hubbard systems. And lastly, recent work in my group has been looking at how to leverage aspects of alkaline earth atoms for new quantum information paradigms. So in this talk, I'm really going to focus on this center topic here, but I also want to give a flavor for what it is about alkaline earth atoms that's actually particularly enabling of all these different directions. So that actually defines the scope of my talk. I'll first talk about alkaline earths and tweezers for just a little bit, but in sort of like a broader way. And then I'll really hone in on this recent story that we've been looking at of assembling indistinguishable atoms in an optical lattice potential. Okay, so alkaline earth atoms, you have 2 electrons instead of 1 in the valence shell, and this gives rise to a slew of levels that have slightly different properties than the ones that exist in an alkali atom. Namely, there's the fact that you have so many of these levels. There's the fact that some isotopes have a nuclear spin that can be used for storing information. Importantly, also, the excited states in the alkaline earths, the low-lying excited states, have a range of different lifetimes and associated transition line widths, which is distinct from what you have typically in an alkali atom, where you really just have the D1 and D2 line with a particular line width associated with it. Okay, so let's walk through how these different transitions can be used for different things. So first of all, there's this transition here. This is a narrow line transition typically that's often used for cooling. We heard about some of that from Manuel. And in certain species rather, there are line widths of 10 to 100 kilohertz, which means you can do efficient, that is rapid, high fidelity cooling of single atoms just based on laser cooling. And this basically impacts any application in which you care about the temperature of the atom. Furthermore, combining this cooling, this high efficiency cooling with scattering off this blue transition here, can give rise to high-fidelity detection, where you can not only discriminate whether or not you have an atom very well, but furthermore do so with very little loss. So this has been used in the context of many-body physics. Our group has also used it in the context of metrology, so that we can recycle the same atoms over and over again. Okay, so these techniques will play a key role later in the talk. Another nice feature of alkaline earth atoms is that they give you a couple different qubits to work with. So for instance, one qubit that we focused on is stored in the nuclear spin. So there are many atoms that have a nuclear spin that are alkaline earth atoms. And in particular, one special one is ytterbium-171, because it has a spin 1/2 nuclear spin, which means it is a spin 1/2 two-level qubit, which is great. So my group, and also beautiful work from Jeff Thompson's group, we've both been exploring this idea. We were able to see that controlling this qubit, we could have fast, low-error rotations on this degree of freedom. Because this qubit can pair with states that are j equals 0, and these j equals 0 states result because you have two electrons, which can pair to kill off angular momentum, that means that you have no hyperfine coupling. So that means all of the violence we do to the atom when we trap it, which relies on doing things to the electron, the qubit doesn't care about. So this means we can have T2 star coherence times of 3 seconds, and actually T1 times of 10 to 100 seconds. Another nice feature is that this narrow line cooling transition can be used in ways that we really were inspired by the Regal group to do low defect loading just via laser cooling, no rearrangement of single atoms in tweezer arrays. So we were able to see 93% loading in 10 by 10 arrays. So if you want to hear more about this story, Alec Jenkins is here, and his poster is tomorrow evening. So it's Wednesday, yeah, tomorrow evening. Okay. So another qubit degree of freedom is on this transition known as the clock transition. This is like a qubit, as I said, but it's a hard qubit, because not only do you need very, very good local oscillators for controlling this transition, you also need to be able to control the atom very well. And this is relevant because you're working with a transition where the atom absorbs a photon, there's a momentum recoil, and that means the motion of the atom really matters. And so we've worked very hard to get to high fidelity control of this optical qubit. And in particular, this has been relevant in the context of metrology, because this transition can be viewed as an oscillator with a ridiculously high quality factor. Both Manuel's group and my group have explored the idea of tweezer clocks. So at JILA, in a collaboration with the E group, we've been looking at how tweezer clocks might strike a balance between the single particle isolation that you have in trapped ion experiments and maybe to approach the scalability of what you have in a lattice clock. So in recent work, we were able to see coherence times of tens of seconds. So in ensemble, we have 19 seconds, and at a single atom level, using microscopy techniques, we can tell that we have 48 seconds of coherence time. And furthermore, we can combine this coherence with new techniques for scaling the number of atoms that we can interrogate to reach stabilities that, at the time of this work, was on par with the state of the art. Since that time, the lattice community has very quickly been pursuing coherence times at this scale, and later on today, we'll hear about work from Szymon Kokowicz's group, where they use the high precision afforded by long coherence times and large number of atoms to measure things like redshifts, which have also been observed at JILA in June's group. A really nice direction that we've been excited about for some time, and a number of groups are excited about these days, is combining this tweezer clock capability with Rydberg interactions, which at this point need no introduction based on the very nice talks we just heard. The key point is that we want to use this to implement operations that entangle the atoms, that we can combine entanglement with an optical atomic clock. So this allowed us, for instance, recently to show for the first time Bell states on a neutral atom optical clock transition, something which is actually now standard in trapped ion systems. And furthermore, this is, I should say, preliminary data, we've been able to see that we can use Rydberg dressing techniques to realize squeezing in an ensemble of atoms. So if you're interested in this, you can go to Aaron's poster yesterday. Okay, so in all seriousness, if you have more questions, we're happy to talk. So that's what I was going to say about alkaline earths. I'm going to hone in now on this story, this short story that we've been recently looking at. So this echoes some of the themes from Manuel's talk in the sense that I want to zoom out a little bit and just talk about quantum simulation with neutral atoms and various considerations that arise given the platforms that people use. And in particular, I want to focus on this challenge of combining scalability with control. Not always needed, but it's one particular thrust these days. And this is exemplified by two platforms, namely quantum gas microscopes and optical tweezer arrays. In quantum gas microscopes, we have the ability to detect and control individual neutral atoms in an itinerant system, typically a Hubbard model. Whereas in tweezer arrays, the atoms, not always, but often are pinned in space, and this can be used to engineer high-fidelity spin models, as we just heard about. I want to take a little bit of time to get under the hood here and just think about what are sort of broad, slightly general descriptions of how these systems compare. So in a quantum gas microscope, we might have thousands of atoms, whereas tweezer arrays, hundreds of atoms, though people are pushing on this. In quantum gas microscopes, because of finite temperature, you might have percent-level defects in a Mott insulator, whereas in tweezer arrays, you can feed back and rearrange the atoms so that you can get to much less than 1%. The geometry that you have in a microscope is typically set by the lattice potential in which you work, whereas in a tweezer array, you can sort of program the geometry that you have in either shot-to-shot or even real time. And finally, in the microscopes, one might have 10 to tens of second cycle time, although we'll hear from Marcus on Friday about even faster experiments. And in tweezer arrays, typically you have less than or much less than a second cycle time. So why do I bring all this stuff up? So there have been a lot of efforts in the community to sort of diagonalize on all of these different criteria to basically prepare systems that are optimized for specific things in that matrix of considerations. So, for instance, in the microscope community, there's this beautiful technique that I think, at least colloquially, I call cookie cutting, where you project an optical potential on top of a defect-free array, and you cut out some sample of atoms. This is nice because you have a higher chance of getting a defect-free sample. And furthermore, if you care about high-fidelity many-body physics, this finite system gives you better gaps. One challenge here is that you still sometimes have residual defects, which can impact the data rate, the time it takes to average down some observable of interest. On the flip side, we have tweezers now trying to do itinerant experiments. So in Cindy Riegel's group and Salim Yochim's group, and more recently in Wasim Bakr's group, the goal here has been to try to combine the programmability of tweezers with the itinerance seen in microscope systems. One challenge here is getting all of these tweezers to be balanced at the level where the tunneling can be coherent across many tweezers. I want to highlight as well work from Dave Weiss's group, and before him, Dieter Mescher's group, where programmable lattices are used to shuffle atoms around to do a variety of different experiments. Okay, so the topic of this talk, or the second half of this talk, is on a technique that we've been pushing on and really was one of the key motivations for our experiments from the beginning, which is basically to smush these two technologies together. So we have a lattice of atoms that are in a 2D plane, so that's these blue balls here, trapped in a 2D lattice and another lattice in the other direction. So basically, this is a plane of atoms that's three-dimensionally confined, and overlapped and registered with this potential is an optical tweezer or an optical tweezer array. For the physics that I'm going to describe, this is strontium-88, so you can think of it as like a photon in the sense that the interactions are 50 times less than what you have in a typical rubidium experiment. Furthermore, I want you to think of this lattice potential as basically a beam splitter network. Each time the atom tunnels, it has some chance to tunnel or not tunnel, in the same way as a photon has some chance of being transmitted or reflected by a beam splitter. Okay, one other essential ingredient that I want to focus on here, because we spent a lot of time on it, is using this narrow line transition specifically in strontium, which has the property that the line width can be much, much less than the track frequency, the typical confinement of the atoms, which means that we can do resolved sideband cooling, a technique pioneered in trapped ions, and specifically what I mean is driving a transition where we reduce the quantum number, allow the atom to decay, and do this many, many times. The typical motional occupation after such a process is fundamentally limited by the ratio of the line width to the track frequency squared, which has the implication that in our experiments, we expect that we could get three-dimensional ground state fractions just by laser cooling with 98.5% probability. Okay, so how do we combine all these features in an experimental sequence? So we start by loading a tweezer array. This is sort of an ugly image, but these are what our images look like in the tweezers that we use here. This tweezer array defines a 2D plane of our atoms. That's how we start with a 2D plane. We then implant this tweezer array into a lattice potential. And so this is an image here in which we actually do this many, many times and drag the tweezer array across the lattice so that we can see the underlying trapping sites in which we might load the atoms. So this picture emphasizes the scalability of this approach. We then use the same tweezers that initially loaded the atoms to rearrange the atoms in the lattice. So we can make images like these here. On the top left is an image where we make 1D tubes of nearest neighbor atoms. On the right is an image where we do every other site. This is where we try to get as many atoms as possible. This is strontium-88 pointing at a strontium-88 atom. So after we do this rearrangement, we then do resolved sideband cooling, and we see spectra like this. I don't want to go through this spectrum. I just want to say the takeaway is that this allows us to do thermometry, and we have a greater than 95% 3D ground state fraction, basically based on the noise that we observe near the red sideband. We then allow for tunneling just by dropping the lattice, and then we detect where the atoms are again. OK, so let's first look at what happens if we just have a single particle. So we can implant an atom in the center of the lattice, that's where this circle is here, and take many runs of the experiment. And we accumulate density distributions like these, which nicely match what you'd expect for just the theory of the simple system of a single atom in a band structure. We can take this tunneling out to long times and observe delocalization of an atomic wave packet over more than 200 sites. We can even do these experiments in parallel to improve the statistics further. One point that I want to highlight is that not only can we control where we place the atoms, but we can in real time modify the tunneling dynamics to implement controllable unitaries on the atoms. And we used this recently to, for the first time, implement this proposed protocol for spatial search by quantum walk by Childs and Goldstone. So if you're interested in this, you can look at our manuscript. OK, so the story that I want to hone in on in my remaining time here is this idea of basically how good are we doing. Specifically, we want to know how indistinguishable are the atoms that we implant into this lattice. And this will be informed by a seminal experiment in the quantum optics community. For some of you, you might be surprised that I'm even talking about this again, because I've spent a lot of time on this physics, but bear with me. And so this is Hong-Ou-Mandel interference, in which photons are incident on a beam splitter. And when these photons are perfectly overlapped in this beam splitter, the photons always come out the same port. They never come out different ports. But which port that is that they come out is fluctuating. So this is the famous example of a dip in the coincidence counts. And this arises due to a path interference phenomenon between the likelihood for both photons rather to be transmitted and both to be reflected. And this is the Hong-Ou-Mandel dip signal, which arises for the particular position of the beam splitter where the photons are perfectly overlapped. So we would like to get at this physics. We have a couple challenges. The first is we can't measure more than one atom on a site. We can only measure parity above that, a common problem in quantum gas microscopes. Furthermore, we really want to be able to see the indistinguishability here, which means we need wave function overlap. So those seem to be competing issues. And so the lead student on this project, Aaron, had a very, very clever idea for handling this, which is basically we operate our quantum walks in 2D, which means that there are more modes than the number of particles squared. So m is greater than n squared, where m is the number of modes. But we can analyze the data in a projected 1D space because the Hamiltonian that these atoms are tunneling in is completely separable. So for instance, we'll have some input state where we have two particles on neighboring sites, and then we see some density distribution at later times in 2D, and projected into 1D, it looks like this. We can analyze the data in mode space just with the occupation of different sites, rather different columns, associated with just the number of atoms that we find in that column. So for instance, we start with this state here, like this one, and then we end up in some distribution afterward. We can then form a correlation map inspired by pioneering work in Marcus Greiner's group and also Philip Price. And the idea here is that I'm plotting the likelihood that we measure an atom at x1 and x2. So for instance, in the input state here, we have a point right here. And if we wait after tunneling and analyze the data here, what we see is a distribution like this, where I want to highlight that at this point here, which was the input configuration, which is where we had two atoms on neighboring sites, there's suddenly a dip in the probability. That is to say, the coincidence counts associated with measuring the atoms in their input configuration has gone away. And so this smells a lot like Hong-Ou-Mandel interference, but in this multi-mode condition of atoms delocalized over many sites. We can check this intuition by, instead of preparing atoms on neighboring sites like this, we prepare them like this, so that now they are offset by 1, and so these atoms are basically distinguished in that y degree of freedom. If you wish, you can think of this whole experiment as basically we have an atom with or atoms with internal degrees of freedom. They're Rabi oscillating, but those Rabi oscillations are synced up while they're quantum walking in the other dimension. And in this particular experiment, what we're doing is starting those Rabi oscillations where one of the atoms is in a different spin state. Okay? So when we do that, we see a restoration of the probability to be in the initial input configuration. And so inspired by just sort of the many experiments now that rely on using purity, deducing purity based on Hong-Ou-Mandel interference, which specifically gives you the trace overlap between the density matrices of two different atoms, or photons, whatever you wish. We can look at the ratio of the likelihood of indistinguishable events to distinguishable events, and we've worked with Manny Knill and Scott Glancy at NIST to sort of formalize this idea. And we can see a Hong-Ou-Mandel dip that tells us that we have a purity of single atom preparation of 96%. And I want to highlight that this comes on the heels of many experiments that have been looking at atomic Hong-Ou-Mandel interference. Okay. So our goal here is not 2 atoms, it's more than that. And I just want to highlight that even in this limit of non-interacting bosons on a lattice, this is sort of complicated. So you can imagine this as follows. So I have some initial configuration, and I might have some final configuration. And let's ask the question, what's the probability that I go from this initial configuration to this final one? These are indistinguishable particles, and they're undergoing just a single particle unitary. There are no interactions, so really all that we need is the single particle unitary that tells me the likelihood that a particle goes from mode J into some mode K, and really the quantum amplitude, I mean. So if I want to do this calculation, I need to think about all of the many particle paths that contribute to this particular trajectory. I have this one here, I have this one, I have this one, and there are many others. There are, in fact, an n factorial, where n is the number of atoms, that contribute to this all of these paths coherently, because they're all indistinguishable bosons. This is, of course, if you're familiar with this field in quantum optics, goes back to the idea of calculating a permanent of a matrix, where this matrix M encodes all of the possible paths by which you can end up from this configuration to this configuration, and then by taking the norm squared of the permanent, you're able to coherently add up all those things and compute a probability. If the unitary U that describes the system is Haar random, this is the problem of boson sampling, which has motivated many experiments in photonics, and in particular, there's been work in Jiawei Pan's group where they've shown 14 photons on 60 modes with successful events of 6 events per hour, and also squeeze state inputs that have higher frequency and are a bit more forgiving on experimental details. And there they've had 50 states on 100 modes. Okay, so this motivates the idea, can we go to later times where the tunneling has occurred over more modes? Furthermore, we care about getting to more particles. So if we wait to later times, we see distributions like this, which agree very nicely between just the distinguishable inputs between the data and the theory, and also indistinguishable inputs, and even instead of going nearest neighbor, we can do next nearest neighbor, and we see distributions like this. So that's good. And this should remind you of work from Marcus's group where they were looking at bunching in these density distribution, in these correlation maps. Furthermore, we can go to more particles just by rearranging more atoms, and the output distribution looks like this. And the key point here is that sampling from m modes of n bosons, that means you're sampling from a distribution that is extremely large. In particular, for 8 particles on 15 modes, we're talking about more than 300,000 possible configurations that we would need to sample if we wanted to know the possibility of any particular configuration coming out. So that's hard. And this has echoes of what Manuel was talking about in his talk as well, in the context of spin models. Let me highlight as well that while I'm showing this projected 1D space, in 2D, this is more than 10 to the 14 configurations. So obviously, no one's going to be doing that. So we can rewind a little bit and ask the question, are there characteristics that we observe in the data that suggest particular metrics that might be more easy to get, or sort of easier to access? So for instance, if we look at n equals 3 particles, And we form these same correlation maps here, but now we're looking at the possibility to have a particle at x1, a particle at x2, and a particle at x3. We see bunching along the effective diagonal in this n-dimensional space. Okay? So this suggests both that the likelihood for the atoms to end up in the same output modes is bunched. Furthermore, beyond that, it shows that the likelihood to be near the diagonal of this n-dimensional cube, basically, is enhanced. So we can look at such things in our data. So for instance, we could look at bunching as a function of atom number, and we see very good agreement between indistinguishable atoms and also what we would expect for distinguishable atoms. And furthermore, there have been some very nice results showing that the ratio of the number of events for indistinguishable particles versus distinguishable goes up like n factorial, and that nicely comes out in these data. We can also look at something known as clouding. This is an idea that comes out of the photonics community, which again is the likelihood that the atoms are sort of close to this diagonal in this n-dimensional space. And here too, we see decent agreement. I want to highlight that as we go to a larger atom number, the fact that we stop this calculation has nothing to do with some like supremacy result. This is just because we're being careful about systematics associated with real collisions on the 2D space that we're still thinking about. So these measurements motivate looking at different kinds of metrics for certifying that you have many particle indistinguishability as you add more and more atoms. So it's sort of an orthogonal perspective to the kinds of things we were hearing about in the last talk, in the sense that this is really talking about indistinguishable bosons hopping as opposed to a spin model with long-range interactions. Okay, so as an outlook here, we can prepare more atoms, we can let them tunnel. What do we do with this? So let's first ask the question, how big can we go? So based on the measured purity that we have of 96%, which we think is limited by our cooling along this axial dimension, we can say that for n equals 50 atoms, we'd have a 12% purity, which is actually pretty good for a system of that size. And also, this can be on 200 modes. We don't see sizable decoherence or dephasing as the atoms tunnel. So we think that this kind of purity will be preserved at late times. So the future opportunities for this kind of system, and I think there are actually a number of people in the audience who are also thinking about this kind of technology, include actually doing boson sampling with atoms. I'm not especially keen to show a quantum supremacy result, but I nevertheless find the physics of this ridiculously simple system and the fact that it's complicated, I find that interesting. So if we apply random unitaries projected on top of the lattice, we could get at this physics. We could also look at Hubbard physics by switching isotopes to strontium-86. We could look at entanglement entropy measurements by projecting potentials on top of this lattice. And we could even think about switching to fermions. So this, in general, strikes me as a new path to getting at the physics observed in a quantum gas microscope, but combined with the nice features of tweezers. I also just want to zoom out in this last 1 minute here on just beyond Hubbard physics, how this technology of a hybrid tweezer lattice could be useful. So in our work in quantum metrology, it was very important to have high fidelity control of many, many optical qubits. And this meant we had to tightly confine them. And so this lattice potential actually gives us the ability to do that, allowing for rotations like this where we have 99% contrast. Furthermore, the length scales of a lattice allow us to get to things like Rydberg dress models and Ising models where the interactions extend symmetrically over many atoms. And finally, rearranging over many accessible sites could be useful for large 2D spin models, ranging from Rydberg physics and also things like Anna was talking about yesterday. So again, this could be useful for a lot of stuff. Okay, before I close here, I just want to make a quick plug for a new experiment, which is a collaboration between myself, Cindy Riegel, and Dan Slichter. Ting Yu is here, who has a poster, and this is an experiment where we are trapping tweezer arrays in a cryogenic environment. We just got our first 3D MOT inside of our cold box. This is a complicated, difficult experiment, and you can talk more about it with Ting Yu. Okay, so with that, let me close. I want to, in particular, highlight the Strontium team who contributed to this work, and in particular, Aaron Young, who is the lead student on these experiments. Also involved, and were very important, were Will Eckner, another grad student, and Nathan Shine, a postdoc. Nathan is off to UMD and to JQI shortly. Thank you.
you, Adam, for this exciting talk. It's time for questions. Yes, we start with Bill.
Okay, so I want to ask about the experiment where you're essentially seeing Hong-Ou-Mandel on this lattice. So you start off, as I understand, with two atoms on adjacent sites. You let them propagate, and because of the Hong-Ou-Mandel type interference, you can't get back to where you started.
The configuration in which you started.
Right, the configuration in which you started. So that sounds fine, and then I'm thinking, so how does this square with the whole idea of reversibility?
I mean, I could switch the sign in this Hamiltonian and evolve it backwards. I don't understand the question, actually.
Okay, well, maybe it's just a stupid question.
No, I didn't mean like that. I just,
No.
I don't. I mean, like if I have Rabi oscillations on a two-level, let's ignore all the other modes, right? So if I have Rabi oscillations on a two-level system, like if I do a pi pulse, I could flop back down, right?
Yeah.
Okay, so now if I have a two-level system, if I have a double well potential and I have atoms starting on separate sites, that Rabi oscillates between the 1-1 configuration and this 2-0 plus 0-2 configuration.
Yeah.
Okay, so now let's add more sites here. Okay, you can think of basically every possible path that takes me back to this initial configuration, going out and coming back. There's one more path where I go slightly less far, I come back, and then I hop. Okay, and when I hop, if both atoms hop, I get a minus sign on the many-particle wave function, which cancels with that first case.
Yeah, okay, and that's basically the Hong-Ou-Mandel argument, I think.
In this multi-mode configuration, yeah.
But, I mean, basically what I'm trying to do is to relieve my discomfort with the idea that Hong-Ou-Mandel argument seems to be inconsistent with the idea that if I went out, I could come back. Now, you're saying reversing the Hamiltonian, changing the time, but I mean, tunneling forward and back is pretty much the same thing, so what am I missing?
I think maybe we should talk more. Okay. I don't totally understand the question. I mean, there are phases on the wave function in the other modes too, right, that matter for the direction in which you'll tunnel.
Okay, we have a question over there.
Thank you for this nice talk. I was wondering, because you mentioned some challenges for optical lattice approach for study Hubbard model. One challenge I understand for this Hubbard physics in optical lattice is to reach lower enough temperature such that you might be see more interesting quantum phase. I was wondering, would you mind comment on maybe with this hybrid approach where you'll be able to kind of overcome this challenge?
Yeah, this is a great question. Exploring this question and the answer to it, I would say, is one of the motivations for this work. I think one needs to be a little bit more specific about the particular phase or ground state that you're interested in targeting, and whether or not it can be adiabatically connected to the initial distributions that we prepare. So, for instance, if we prepared a unity-filled system and then we melted, we could make a superfluid from the effective Mott insulator. But if we were working with fermions and we prepared, say, like a spiral of spins in the nuclear spin, and we were interested in making a spin liquid, I actually don't know the answer to that. Furthermore, I'll add that an important consideration is just the purities that we can access. I hope Marcus, if he's in the audience, will forgive me, but if you compare the purities that we're getting to what we had on the experiments that I worked on as a postdoc, these are actually the same, if not just a little bit better. So in that sense, I think that at least in these finite cookie cut systems, these are comparable approaches now.
Okay, do we have a question from students? Did you prepare your question, actually? Yeah, I have one curiosity. You mentioned in the end about the possibility to study Hubbard physics with isotope 86. Mm-hmm. Means that now you are using the 88 to suppress interactions.
That's right.
Okay. Okay, we have a question from Manuel here.
projection, I'm still wondering about the parity projection and how you get rid of. I mean, in the end, you add up all a bunch of tubes, but you still have a parity projected signal in the end. I mean, it's not getting rid of it.
And that was at the bottom of one of these plots. So there is still some probability of a collision in the 2D space. So at the Hong-Ou-Mandel time, that's about 13%, which agrees exactly with what we'd expect if we calculate the 2D quantum walk. But because we're projecting into 1D and just counting the number of atoms that we have in each column, for the main signal that we're looking at in 1D, this effective 1D space, the incidence of these collisions is much less. Does that make sense? So in the 1D projected space, if you had to throw away all of your data each time you had two particles in the same column, that obviously would be unhelpful. But because we're really in 2D, but projecting into 1D, the incidence of real collisions is reduced.
I think I get it. I see.
Okay, are there further questions from the audience? So if not, let's thank Adam again, as well as the speakers of the session.